So today we're going to work on derivatives of sine and cosine, as you can clearly see by the title of today's topic. Before I do that, I want to do a little bit of a review of what we're covering in this section here. I really like to think of things as either polynomial functions or non-polynomials. And hopefully you'll remember that polynomials will fit the pattern, something like this: y equals 7x to the 4 plus, maybe there's 0x to the 3, and we don't bother writing it. And there's 2x to the 2, maybe it's negative x plus 7. That's your standard polynomial. And I mean, polynomials could have been written like this: 2x squared plus 4 bracket x to the 3 minus 7x plus 1. And you could have needed to FOIL it out and distribute it. Those are your polynomials, right? And the reason why I mention those is because when we want to find the derivative instead, usually you're doing one of the following things. You're doing, like, say, a power rule, where you're dropping the exponent down in front and then multiplying and dropping the exponent down by one integer. So you could do the power rule. You could be dealing with your addition and subtraction rules. Like in this one right here, you could have to FOIL and know how to use your product rules, or maybe your division rules. You may need to do a chain rule, right? Because perhaps a polynomial could have been 3x squared plus 7 all to the power of 7. Right, and there's like a chain rule involved there. And if you wanted to distribute it, you could. Not that you'd want to, that'd be crazy. But this essentially is a polynomial, right? So that's where we began our talk of derivatives. Now we're going to talk about finding derivatives of your non-polynomial functions. And just like we did in our polynomial section, we really need to refer to limits, because limits are the whole reason why this exists. So I want to do a bit of a review as to what we would have covered way back in our derivative section. If you were to have a random point right here and another random point right here, if you were to bring this one closer and closer and closer to this one right here, if you were finding a secant line that goes between the two of them, if you wanted to find a tangent line instead, it would work way better if all of a sudden this point that was up here was basically side by side, and then now they're basically touching, right? And since they have to be basically right on top of each other, nearly the same thing, this is where limits come in. You find the limit as, say, your P approaches your Q, and you have this one be P and you have this one be Q. Or you could do your limit as H approaches 0, and the distance between these guys is H. And so that's where we have to start. And even though we're going to find rules for sine and cosine, and we're just going to now know what they happen to be, it's important to know how we achieve them. And so before I even do that, as I'm continuing doing a review, I should remind you what we did last lesson. We talked about a couple different properties. We discovered that if you have the limit as x approaches 0 for sine of x over x, that was equal to a value. And if you have the limit as x approaches 0 for cosine of x minus 1 over x, that was equal to a value as well. Right? And we also talked about things like how to do the limit as x approaches 0 for, say, the number 2. That's also just equal to a value. And if we give you x approaches 0 for just, say, like sine of x, that's equal to a value. Right? And so let's just do a quick recap of what those were. I won't go through the proofs of all of them. This first one, the proof was on a page in a textbook. If you happen to have a textbook nearby, hopefully you've seen a proof for why this one works. It's known as the squeeze theorem as to how the proof actually existed. But long story short, we now know that this is equal to 1. And that has been proven, and we can just use this going forward if we'd like. And then this one right here, we did a proof in our notes just the other day, and we actually managed to prove this equaled 0. And so those are ones that we did some proofs for. This one right here, I don't know we really need a proof for it. Here, x approaches 0, but it's going to be 2, right? It's just a constant. And then on this one here, you could just say that it's the sine of 0, because you could just plug in 0 for x. And this one right here, I should point out, this really works for anything. This could involve just x squared plus 7. That'll be 0 squared plus 7. All you're doing is you're just plugging 0 in for x if you want to. So these are some of the rules that we can work with our limits when we try to find now the derivative of some of our non-polynomial functions. And some of the things we're going to cover for our non-polynomial functions will be anything involving trig, which is basically your sine, your cosine, your tan, as well as their reciprocals, which will be cosecant, secant, and cotan. We're also going to talk about how to derive things that are exponential, which would be like, say, 2 to the x. And then finally, we'll talk about how to derive logarithms. And logarithms would be things like say, log x. And then the other one we're going to talk about is ln x, ln(x), which is known as the natural logarithm, which many of you, I imagine, have never heard of a natural logarithm before. And if you have, that's awesome. And if not, we'll talk about it in this course. So let's get to our proof. We want to try to calculate the derivative of sine. So we're going to use this definition here, which is our first principles, which I've had you do before on your midterm and on some of your assignments. So let's give her a try. The way this would work then is we're going to do the limit as h approaches 0 for sine, but now rather than being x, it's going to be x plus h. And then we're going to subtract sine of x, and we're going to divide by h. And there we go, we're done. I mean, that's literally all we can do. Well, no, it's not if you know some more of your rules. Right? In order for us to figure this out, we actually have to know one of our identities. And I had a sheet of identities earlier. There's a rule basically that says that if you have sine of a plus b, you can change it into something. I believe I have this one correct here. It turns into the sine of a, then the cosine of b, and then it's plus the cosine of a sine of b. And hopefully that's a rule that you've seen before. It's known as an identity. It's a little trick we can play. Because if it wasn't for that little trick, we'd be stuck right here. There's not much more we can do, but now I can use that rule. So if you've done your 30-1 already, that identity means we can change it to this. This will be sine of x, and then the cosine of h, and then it'll be the cosine of x and the sine of h. We're going to minus the sine of x, and all of this is being divided by h. Okay, well, the next thing I'm going to do is I'm going to do a little bit of factoring and rearranging here. The reason why I'm going to say factor, before I even factor, I'm just going to rewrite this a little bit. I'm going to rewrite some terms that are similar to each other. And really, the only two similar terms I have are these two signs, which have sine of x in them. So I'm just going to put them next to each other. I'm going to do sine of x, cosine of h. And then I'm just going to put the negative sine of x next to it. And I'm going to divide all that by h. That works. I'm just putting this guy next. And then I'm going to do two things in one. I mean, this middle term here that I haven't worked with, it still also exists, which means I really need to then have my cosine of x and my sine of h. But I also need that to divide by h as well. And I figure while I'm at it, why don't I just separate these using a limit sign right now? So that'll be h approaching 0. So if you're able to follow what I did here, I just took this guy and put it next to this one right here, and it needs to be divided by h. And then I just took this middle term right here and put it last. I gave it its own limit sign and divided it by h as well. Now, I mentioned just a few minutes ago, the reason I'm going to do this is because I want to try to factor. So I can factor out sine of x, and then it would leave me with cosine of h minus 1, and that would be over h. And then over here, I'm going to do a couple of things as well. I'm going to separate this even one more time. I'm going to give each of these an independent limit sign. And so I'm going to now apply the h with the sign, but I'm going to leave the cosine one by itself. So I'm going to give cosine of x to go right here. But then I'm going to apply a new limit sign to the remaining bit, which is sine of h over h. Hopefully you can see how I did that. This h right here, it gets to go with either one or the other one, right? This h right here goes with this term and with this term and with the last term. But now that they're being multiplied by each other, I can choose who gets the h. So I'm going to give it to the sine h, because hopefully you'll see the reason why I'm going to give this one right here is that sine h over h, we just did that. That's equal to, what was it equal to again? I got to remember. I think it was equal to 1, wasn't it? Yeah, this whole thing right here is equal to 1. So look, I can replace that right there. And in another line down, right here, look, the limit as h approaches 0 for cosine of x. Well, we need to almost consider cosine of x just to be a constant term. As h approaches 0, I'd plug in 0. But there's nowhere to even plug in h as 0 for, so I could just call this guy cosine of x. It's kind of like this thing right here was a 2, and I just left it as a 2. Only it's cosine of x. I mean, x is a variable, h is a variable, but they are different variables from each other. So I'm doing pretty good over here on the left-hand side. Well, that's the right-hand side. way over here on the left-hand side, I have a little bit more work to do. I'm going to break it up so that I get sine of x right here. And then afterwards, I'm going to times it by the limit as h approaches 0 for cosine of h minus 1 over h. So I'm going to apply the h to the cosine of h minus 1 side. And I'm going to leave the sine x by itself. And it does not get to be over h because the h goes over 1 or the other one. But I would remember that this guy right here, we just learned that guy's equal to 0. Right, that was another rule we learned in our previous lesson. And so I can replace the whole thing with 0. And over here, if I want to plug in h as 0, that's fantastic because there's nowhere to plug in h as 0. So this guy right here would just be sine of x. But honestly, that doesn't really matter because the whole thing was timesing by 0, so it's all gone. So our final answer is cosine of x. And I mean, times by 1 is kind of redundant. So here's what this means. If you were to take the derivative of sine of x, it's equal to cosine of x. And that is a rule that we will now be able to work with going forward, is the derivative of sine is cosine. So we can actually kind of see that if we look at it graphically. I want to talk about the parameters of this sine graph, which for me it's in blue. Look right here. What's the slope right here? Well, the slope right here is 0. And look, the cosine graph is 0 right there. Now look, what sort of slopes is it right here to here? Well, the slopes in all of this section right here are negative. Well, look at that. The cosine graph is all in the negatives. Until you get right back to here, where the slope is 0. And look, this graph right here is at 0 right there. Well, now, this graph all has positive slopes, right? All the way along here, it's positive slopes. Hence, this graph right here is positive. I like to joke with my Math 30-1 class that a cosine graph is a sine graph that like failed a grade because it's a little ways behind. Now, this point is always just a little ways behind this point, and this point is always a little ways behind this point, and it's always one grade behind from here to here. It's always playing catch up. But another way of approaching it is that the cosine graph is really the derivative of a sine graph. So there's a property we're going to use whenever you need to derive sine. We'll make it into cosine. Okay, well then, if we're looking for the derivative of cosine, we should also look for the derivative, if we're finding the derivative of sine, we should also find the derivative of cosine. And so we're going to prove this one as well. We're going to use the identity, though, cosine of x equals sine of pi over 2 minus x. That's like the little trick we're going to play to make this work. So if we're going to try to pull this one off here, let's try this. So if f of x was supposed to be cosine of x, before I even derive it, let's play a trick. I gave you the analogy that cosine is sine, but like it failed a grade, it's behind by a section. So really that's where this notation comes from here. Okay, so what ends up happening here is that this is really pi over 2 minus x. Your x value is behind by pi over 2, hence the whole idea of really this one is catching up by pi over 2 from here to here. And hopefully that kind of makes sense. This is an identity we can use. It's actually not one you probably learned on your formula sheet, but hopefully that makes sense. A cosine graph is a sine graph that's like behind by pi over 2. So if this is my original function, before I even derive it, let's change it to sine of pi over 2 minus x. Well, now if I want to derive that function, we now know what the derivative of sine is. The derivative of sine is a cosine of x, with one problem. I didn't have x in here. I had pi over 2 minus x. So that requires a chain rule, which means I'm going to have to chain on the derivative of that baby inside, which is the derivative of pi over 2 minus x. Well, based on that, it's cosine of pi over 2 minus x times by, and then the derivative of this right here is just, that's a times sign, is just -1, which leaves you with negative cosine of pi over 2 minus x. But really, if cosine failed to grade as sine, then doing that again should get you kind of back to sine again if you do that like another way. And so really, this thing right here is really just back to being sine again. So here's the rule, basically. If you derive cosine, it actually gives you negative sine. And that's essentially the proof for it. Remember, basically this and this are my analogy of like failing a grade, falling behind by 1 set of pi over 2. This one right here is fallen behind by a pi over 2. So, well, hopefully that made sense there. Long story short, I now have 2 new rules for you. If you want to find the derivative of sine, make it cosine. And if you want to find the derivative of cosine, make it negative sine. Now, when I was in university, I had to memorize these, and I didn't give them to you on a formula sheet. And I will give you these on your final exam, and you can always look it up on assignments, but I very distinctly remember having to memorize all of the non-polynomial derivatives. So you had to memorize the formulas for logarithms and trigonometry and exponential stuff. And so it wouldn't hurt for you to start to memorize some of these rules, but don't freak out right now if you need to look them back up again. Okay, that'd be something you're allowed to do. One more thought here is that when it comes to these 2 functions here, we still can use product rules, chain rules, power rules. Those still apply as well. So yeah, let's give some typical examples here. Let's try to differentiate these guys here. So if I want you to find the derivative of sine of 3x, this is basically, it's like a chain rule as well as a sine rule there. The derivative is going to be, well, sine turns into cosine. But then you have to add on the derivative of the 3x, which is 3. So your derivative will be 3 cosine 3x. Okay, well, next one right here, I'll just kind of go down a little ways because I need some room. If I want to find this derivative, the derivative of sine is cosine. So it's cosine of x plus 2. But then we have to chain rule on the derivative of x plus 2. But the derivative of x plus 2 is just 1, so your y prime is cosine of x plus 2. And for this last one right here, same sort of thing. Your derivative will be cosine of the baby inside, and then times by the derivative of x to the 3, which means your final answer will be 3x squared cosine x cubed. All right, I blitzed through those pretty fast. If I lost you there, there's not a whole lot to explain. I'm applying a chain rule along with my sine and cosine rules. Right? Don't forget, sine is cosine, and cosine is negative sine. So if you know those rules, every time that you're being asked to derive a sine, derive it into a cosine, but then still apply power rules, chain rules, product rules, quotient rules, wherever you need to as well. So anyways, if that made sense, that's awesome. If not, rewatch or add it to your list of questions to ask. So let's try this one. Well, what this really means before I even derive it, this is sine of x all to the power of 3. That's another way of writing, if you recall. So if you want to derive this, really the baby inside is the sine. So you're going to make it 3 sine x squared, and then you will derive sine of x, which means that this will be 3 sine squared x. Remember, you can just put the 2 in this location instead. And then deriving sine becomes cosine. And there's our derivative. Yeah, I don't need you guys to be able to reprove the proofs for sine and cosine. If you're able to follow them, that's fantastic. What's more important is that you know how to apply those rules. And so we're going to have a big list of rules. It wouldn't even hurt to just grab a sheet of paper and call it your formula sheet and have these 2 derivatives right here be on there, because we're going to add to it. We're eventually going to do tan, and we're going to do like cosecant, and eventually we're going to do the derivative of a logarithm, and we'll do the derivative of pretend that's not there. We'll do a derivative of like an exponential function, right? And so it wouldn't hurt just to make a sheet that has kind of like what all these derivatives become, if you'd like. So, okay, let's try this guy. What this really means is that there is a sine of x squared minus 1, and all of that is cubed. So in a way, this is like one of those baby inside a baby, the Russian nesting doll examples. So let me know if I lose you, and ask me questions afterwards. So here's how this will look. It'll be 3 sine of x squared minus 1 squared, but then you'll have to derive the sine of x squared minus 1. So that first part doesn't really change there. When you derive the sine of x squared minus 1, it'll be the cosine of x squared minus 1, but you'll still need the derivative of x squared minus 1, which means final answer, well, actually not final answer because I'm going to clean it up a bit. It's going to be 3 sine of x squared minus 1 squared, then the cosine of x squared minus 1, and this guy here derives to 2x. Hopefully you could follow that. I mean, the hard part really is the chain rules. But hopefully you're able to follow that sine turns into cosine. That's the only new thing we've learned. So last step here, let's clean it up a bit though. To find our derivative, you could call it 6x. Then you could call it sine squared x squared minus 1 and cosine of x squared minus 1. And that would be kind of your final answer. Now, you are going to want to ask your teacher, professor, to what degree do you want it simplified? I'd be okay if I don't say to simplify, to leave it here because all your derivatives have been taken. But chances are you're going to be asked to clean it up a little bit. My standard preference is I put coefficients in front, and I put like x's next, and then I put like, say, sines and cosines in like some sort of logical order so that it feels like it's kind of split up. So, okay, let's try this one. This one involves a product rule. Because if you want to derive this, really, you've got an A and a B. You've got two different pieces going on here. So to make this one work, the product rule is, say, first derivative second plus second derivative first. So you have two derivatives to take. You've got to do cosine, which is negative sine. We just learned that a few minutes ago. And then here, derivative of x squared is 2x. Last thing I do, I might clean it up a little bit. So I'm going to call it negative x squared sine x. And I'm going to add 2x cosine x. I'm just going to change the order I write it in. And hopefully that's clear why. I want to throw this like in front so that I don't happen to think that you're like cosigning 2x squared. That'd be bad if you accidentally tried to combine this section together here because they are independently different. So I'm kind of flying through these examples mainly because it should be easy. I hope it is. If it's not, make sure you ask me questions. But I mean, the reason why this should be easy is that this is just a product rule, which we've learned before. And the only new piece is that if you see a cosine, make it negative sine. So this is a part of calculus where a lot of kids like it, where if they've wrapped their head around it and they get what they're supposed to do, it's just learning a bunch of new rules. And I mean, it can be confusing if you don't have the background skills up till here. But if you have learned your product rules, your chain rules, really we just add a new brick at a time as we build kind of your calculus, I don't know, building, right? One brick at a time until we get everything put together. So, well, we can even do implicit differentiation. So I've been showing you how to do, like back here, these were some chain rules. Here there was a product rule. We can even differentiate this. We'll just differentiate it like we did implicitly. So I'm going to find the derivative of sine of x plus sine of y on one side. And I'm going to find the derivative of 1 on the other side. Well, derivative of 1 is 0, so that side's easy. So it really, I need to find the derivative of each of these guys independently. So sine x becomes cosine x. Sine y becomes cosine of y. But hey, we were deriving with the wrong variable. So you need an extra dy over dx. Kind of sitting at the end here. Which means that to find dy over dx, you're going to have to subtract the cosine of x to the other side and make it negative. And you'll have to divide by the cosine of y. And so there you go. The derivative of that particular function was negative cosine x over cosine y. Now I got to point out, you can't actually cancel these cosine signs. Hope you guys are all aware of how that works. That's not something that'd be valid to do. So, okay, again, if you have questions, I'm kind of blitzing through these examples a lot faster. Make sure you ask me questions. Some of you don't ask me nearly enough questions about either your assignments or about the notes. So if I lose you somewhere, we can talk through a little bit more in detail. So, okay, so that's my last kind of slide for this section here. I just flipped to the next slide to see what we're doing next here. That's what we're going to do tomorrow. Is we're going to do in our next lesson the other trig functions. So we're going to eventually do tan, cotan, secant, and cosecant. and we're going to find the derivatives of all 4 of those. And I mean, once we do the proofs of them, we'll never do that again, because here are some of the rules for them. And then once you know how to use your rules, then we're just going to do some more examples where we do product rules, cosine rules, chain rules inside there. So you might notice these notes here are a little bit shorter than some of the other notes we've learned, because we've done most of the heavy lifting. We've learned our core rules of how to add, subtract, multiply, divide. We've also learned how to deal with what happens when you have a function inside another function, which is your chain rule. And we've learned how to deal with things that aren't functions if you have to use implicit differentiation to solve for y. So now we just use those 6 fundamental concepts, or however many there are, 6. Yeah. We use those fundamental concepts, and we're now going to apply them to things that are sine, cosine, tan, cosecant, secant, whatever I missed, cosecant, tan, cotan, exponential, logarithmic, and we're going to build our way through all of the non-polynomial functions. One last thought, and then I'll stop the video because I did a pretty good job of keeping this short. Once we've covered that, then our next section is going to be talking about how to apply this to more of a scenario-based thing. Because I promise you that derivatives do have an application, right? And we've talked about that before, right? If we haven't mentioned this in a few videos now, but what is a derivative? Well, a derivative is an equation for slope. I love the economic example here, right? If your example goes like this, and you want to find the slope at any given point, then you find the derivative. Well, what happens if your slope has to be something that's not polynomial? What happens if you're talking about a sinusoidal graph? What happens if the markets are very cyclical? And this was a sine graph. Well, we need to be able to derive sine and cosine just the same way as we need to be able to derive x squared plus 2x plus 1, right? That guy's really easy to derive. Well, now, if I give you sine of x, then the derivative is now cosine. So you just need to memorize these rules and know how to use them. And hopefully you were able to see at least and understand on the first slides how we came up with these proofs here. Okay, so hopefully this slide here kind of made sense about how we were able to use these rules of like sine h over h and cosine h minus 1 over h. Hopefully that made sense. I will still assess you on some of those limits, but those were just used to get us our rules, and now we just use those rules as we need to. So, okay, I feel like I'm just kind of rambling a little bit here, so I'll pause the video and we'll talk again another day.